Okay, so hello and welcome back. So basically in the previous video we talked about basically, I don't really know if we did, but if we have not talked about those things, we will talk about them now. So we have basically three fundamental things in an electronic circuit, or in an electrical circuit, really. If you have basically a simple, for example, if you have a simple, for example, even a lamp, for example, and if that lamp is connected to some DC power supply, negative, positive, and we said that we follow the conventional current flow, and since we do that, then of course the current in a circuit goes from the positive pole of the battery back to the negative. We follow this convention. So this is going to be your current, this is going to be your voltage, and this is going to be your resistance. Basically, there is some resistance in a circuit, there is some current going through the circuit, and there is some voltage. Now, so basically V, I, and R are present here. Now, even if you connect your lamp to an AC power supply, suppose that, for example, you connect that to a for example, even to a signal generator or anything like that. Even if you connect this to an AC power supply, then over here, of course, you're going to have some AC voltage. Here you have a DC voltage. You have some AC voltage here. You have some basically AC current going through the circuit. This is DC current. The current over here is DC. The current over here is AC. But anyway, the current is there, and the resistance is of course there as well. So that is that. So these three things, the resistance, the current, and the voltage, are always there. Of course, in an AC circuit, there is no question of current going this way or that way. It keeps changing because your voltage is going up and down, and something like that, and we will get to that when we get to AC. But since your voltage is becoming positive, negative, and so on and so forth, then the direction of current is changing, basically based on the frequency of your voltage. So it just keeps changing. For example, if the frequency is 60 Hertz, for example, we will get to all of these, of course. If the frequency over here is 60 Hertz, that means that for example, in 1 second, you have basically, that means that in 1 second you have 60 complete cycles. Basically, this would be, for example, 1 complete cycle over here. This over here would be 1 complete cycle, going from 0 to 0 and then 0 to 0 again. So that would be 1 complete cycle. So then what that means is that in basically 1 second, basically in 1 second you have 60 of these cycles. So in every cycle the voltage is becoming positive, negative, positive, negative. So then relative to this, your current is changing here. But of course I'm not supposed to be talking about these right now. But anyway, if in an AC circuit you have basically current, you have a resistance, you have a voltage. In a DC circuit you have a current, you have a resistance, and you have a voltage. And basically these three values are connected together or are related together using some relationship called the Ohm's law. Now Ohm was the name of a scientist, a German scientist or German physicist, I suppose. I don't remember the exact, the complete name right now. But this was basically the name of the physicist. Let me look this up. Oh, here, 1789. The name was George. George in German is sometimes written and read as Georg. So Georg Simon Ohm was a German physicist and mathematician. As a school teacher, Ohm began his research with the new electrochemical cell invented by Italian scientist Alessandro Volta, and then he was born in March 16, 1789 and died in 1854. So around 64 years. He was German. And he has written a couple of books, the Galvanic Circuits Investigated Mathematically, and some other book. That's basically Georg Simon Ohm. And of course this relationship between the current and the voltage and the resistance is one of the most fundamental things in electrical and electronic circuits. Without that you could really do almost nothing really. Now this relationship is simply V is equal to I times R. V is equal to I times R, and what that means is that the voltage is always the product of the current times the resistance. Your voltage is always the product of the current times the resistance, or the product of the current and the resistance basically. And well, as long as we're talking about this formula, voltage is basically the unit for the voltage is volts. The unit for the voltage is volts, and is denoted by capital V, I suppose. It must be capital V. It is capital V. And the current is the unit for that is basically the ampere, and it is denoted by capital I. And I'm sorry, denoted by basically the unit is written this way with capital A. And so voltage voltage itself is denoted by capital V, the current is denoted by I, and resistance is denoted by R. So here you have resistance. Here you have resistance, which is the unit for resistance is ohm, denoted by the Greek letter omega. So this is basically all about this relationship between V, I, and R. And of course, you know enough about algebra. You see there is a, when you say V is equal to IR, there is a direct relationship between, for example, between V and R, or there is a direct relationship between V and I. For example, if you keep your I constant, then if you increase your V, R has to be increased, because otherwise this wouldn't remain an equation. For this to remain an equation, if you increase your V, you have to increase your R, if your I is constant. And of course, if you decrease your V, you have to decrease your R. On the other hand, if you have V is equal to IR, if I keep my R constant, then if I increase my voltage, the current is going to be increased. If I decrease my voltage, my current is going to be decreased, because they have a direct relationship. If it was something like, for example, now suppose that, for example, V is equal to IR, and then, for example, I is equal to V to R, right? So, meaning that if you just simply divide both sides of this equation by R, for example, V to R is equal to IR to R, and then R and R will cancel out, so I is equal to V to R. Now, if that is the case, then you see, for example, I and R have an indirect relationship, or have an inverse relationship, meaning that in this, if you keep your V constant, your voltage constant, when you increase your current, you have to decrease your resistance. Because if you increase your current, then V to R has to be increased. For this to increase, this has to decrease. It's just simple algebra. And if you, for example, decrease your I, you have to increase your R. So this way, even I get confused, you don't need to bother about that. But if you ever need to, sometimes you need to basically analyze a circuit, not basically quantitatively, but qualitatively. In that case, basically, you just need to write the proper equation, and then basically think about, for example, what happens if you, for example, increase your I, or decrease your R, or increase your V, and so on and so forth. But for now, that's not really important here. So then, in a nutshell, basically we said that V is equal to IR. So this is your voltage in a circuit. This is the voltage in the circuit. This is the current in the circuit. And this is the resistance in the circuit. And this is the resistance in the circuit. Now the unit for this, the unit for the voltage is volts, denoted by V. The unit for for the current is ampere, denoted by A, and the unit for the resistance is ohm, denoted by this Greek letter omega. I suppose this is I think this is uppercase omega, because omega can be written this way and this way and this way. One of them is uppercase, one of them is lowercase. I don't exactly know, but this is basically the Greek letter omega. You can look that up if to know whether, I mean, if you really want to know if that is uppercase or lowercase omega, you can do that, of course. And if you let me get you all the Greek letters here. Okay, so these are all the Greek letters, all the Greek alphabet, not probably not letters, would not be the right word. So the Greek alphabet, and omega is basically, omega is the last alphabet over here, and this is uppercase, I suppose. This is the letter used for the unit ohm is the uppercase omega, and then the lowercase omega is something like W in English. So you can make a screenshot of this if you need this. Of course, this is part of some physics book and of course you can make a screenshot of this table as well, because you're going to need it. This is also important. So these are the two things that you're going to need, and so so the unit for the resistance is ohm, denoted by omega. Now the important thing about this formula or this equation is that basically just to get rid of confusion and not making mistakes, whenever you're solving the problem, enter your voltage always in volts, enter your current always in ampere, and enter your resistance always in ohms. And basically when you do so, for example, suppose that when you enter your resistance in ohm and enter your current in ampere, you will always get your voltage in volts. And well, the other way around, for example, if you enter your voltage in volts and your resistance in ohms, then you will get your current in amps. And moreover, there is two other forms of this formula. If I divide both sides of this equation by R, I will get V divided by R is equal to IR divided by R. Then R and R will cancel out, and you will get I is equal to V divided by R. Meaning that is basically another form of the formula. And the same equation, V is equal to IR. Now if you divide both sides of this equation by I, you will get V divided by I is equal to IR divided by I. I and I will cancel out. That means that R is equal to V divided by I. That is another form of this, that is another form of this formula that you can use. So in short, you can say that V is equal to IR. Then you have also I is equal to V to R, and R is equal to V to I. That is basically the three forms of this formula. But if you know this part, then you can always derive these two, and so you don't have to worry about that. Now, there is a couple of examples here that we can solve. And before we start solving these problems, I need to say a few words about rounding numbers. Rounding numbers. Now, for example, suppose that I have some circuit in which my resistance is equal to, for example, 20 ohm, and the current going through the circuit is 0.5 amps. Is 0.5 amps, and I want to calculate my voltage. Okay. Now over here, what happens is that, of course, you know, V is equal to IR, so I take V is equal to I, which is equal to 0.5 in amps, so I don't have to convert it, times 20 in ohms, which is equal to 10 volts. Okay. Now the number that you get here, I think you know from, for example, from physics or from chemistry, that when you calculate something, you have to, I mean, most of the time you're told that you're told to round to 2 decimal places, or to 3 decimal places, or to 4 decimal places, and so on and so forth. Now, of course, there is a reason for that, but then when you take any course in physics, for example, there are all of these rules for rounding numbers. For example, then there is all of this business of the number of significant figures, and then when you're doing, for example, addition and subtraction, you have to deal with the number of the significant figures in a particular way. When you're doing multiplication and division, you have to deal with them in a particular way, and so on and so forth. Now, in electronics, people usually don't do that kind of thing. And the reason for that is that it's not really necessary to do that in electronics, because things are not really that, I mean, at least in the beginning, when you start working with these circuits, things are not really that precise, meaning that there is a whole lot of tolerance and uncertainty with the value of the resistors that you use. There's all kinds of problems with the wires that you use. There's all kinds of tolerance with the power supply that you use. There's all kinds of tolerance with, for example, the test equipment that you have. They're not calibrated, and all of those problems. So then, for example, it doesn't really matter if, for example, you really follow all of the rules of significant figures and rounding numbers. As long as you have some number that you can work with, that's more than enough, at least in this stage, unless you want to, for example, I don't know, design, for example, a circuit, a power supply circuit that, for example, creates a voltage of, for example, 5 volts, for example, exact or accurate to basically 5 decimal places. Suppose you build a circuit, and this circuit generates or regulates a voltage of 5 volts, or give you 5 volts exact to 5 decimal places, meaning that if you, for example, measure that voltage, the voltage would be 5.00000 volts. exactly, without any tolerance. Unless you're doing this kind of thing, it doesn't really matter it's not really necessary to follow all of those rules exactly and do that sort of thing, basically. And once you start working in electronics, basically you will get some sort of feel for numbers, and then you will know how to round your numbers, basically, without really, you would actually be following all of those rules without following them. I know this, what I say doesn't make any much basically logical sense, but what you would be doing is that you're considering all of the tolerance of your test equipment and components and everything that you have. And so considering all of that, you would be basically following all of those rules without actually following them. So that's something like that. And that is basically that is basically getting some sort of feel for the numbers, how to basically round your numbers in every particular situation. Based on the situation, you know what to do. So that's basically that. So that is that. So now if you let's go over here and for example do another calculation here. Suppose that, for example, you have a circuit, for example, your resistor, the value of the resistance is, for example, 560 ohms, and your current is, for example, 0.02 amps. Okay. Usually, and of course, usually in electronics, for example, 560 ohms is okay. Everybody calls this 560 ohms, although most probably this is not the kind of resistor that you would actually get in a resistor. This value of resistor is actually most probably not even in range, but that doesn't really matter. But this sort of value for the current is usually called by people, when people want to talk about this current, they call it 20 milliamps. They usually call it, almost always call it 20 milliamps. And if you had, for example, 0.2 amps, they would call this, for example, 200 milliamps. And if you had, for example, I don't know, 0.002 amps, for example, they would call this 2 milliamps. If you had, for example, 0.0002 amps, they would call this 200 microamps. 200 microamps, and so on and so forth. But, well, we will get to that part as well. For that, you need to take a screenshot of this table and keep it with you. After a while, you will learn all of these suffixes. The most important ones are, which you will use most of the time, is kilo, is mega, is giga, is tera. Is not that important. These are not that important. Milli is important, micro, nano, and pico, and these are not that important. So milli is 10 raised to the power negative 3, micro is 10 raised to the power negative 6, nano is 10 raised to the power negative 9, pico is 10 raised to the power negative 12, and femto and atto are usually not even there. So take you take a screenshot of this and then keep it. You will be using it. Okay, so now suppose that this has been given to you, and you want to calculate the value of your voltage. So V is equal to IR. So V is equal to I, which is equal to 0.02 times 560, and both are, this is in ohms, this is in amps. So I'm going to get my voltage in volts. So that is 112, let me see, 560 times 2 decimal places 10, so 1 decimal place 12, 1, 2 times 112, 11.2, so you get 11.2 volts, for example. V is equal to 11.2 volts. So this kind of thing, for example, you can call it, you can keep it as 11.2 volts, or you can, for example, call it, for example, 11 volts or so. Okay, so of course you're talking about, for example, 20 millivolts, then you're talking about 20 millivolts, for example, then basically, well, you would call it, you would simply call it, for example, 11 volts. Okay, but you can keep it as 11.2 volts. How you deal with your number depends on what you're doing in that particular situation, and you will know that based on the project that you're working on something that needs a whole lot of precision, so you don't throw away your precision. If you don't need that much of precision, it doesn't really matter if it's really 11.2 or 11.4 or 11.5 even. Usually you will just call it 11 volts, and that's basically how you do that. So that is that.